Modern operating systems are heavily fortified against traditional malware, but to extract maximum speed, engineers have built deep performance optimizations directly into the architecture. These optimizations create inherent vulnerabilities within the physical mechanics of the system. As a result, the hardest battles in cybersecurity have moved beyond the network perimeter. Firewalls and packet inspection systems catch external intrusions, but advanced adversaries now target the layers beneath them. The true threat landscape has shifted inward, residing deep inside system memory and the high-speed hardware pathways that connect our devices. Because these vulnerabilities are rooted in the physical behavior of hardware, they create unpatchable attack surfaces. They operate beneath the operating system, rendering standard security controls blind. To understand this threat, we have to examine two specific architectural features: software-based memory deduplication and hardware-based direct memory access, or DMA. Artificial intelligence automates the identification of these hardware signals, transforming historically manual, theoretical exploits into scalable, persistent threats. For IT technicians and security operations center analysts, the implications are severe. Because these attacks bypass the operating system entirely, traditional forensic tools and event logs register no activity during a breach. Defending modern enterprise environments means understanding the physical mechanics of these deep-layer bypasses before an adversary weaponizes them. Memory deduplication is a software optimization designed to conserve physical RAM. It is a standard feature in multi-tenant cloud systems and virtualization platforms, where server space is shared among multiple users. The OS scans isolated virtual machines. Finding identical data across tenants, it consolidates them into a shared physical RAM page. If a process modifies its data, the system physically unmerges that page. This separation introduces a measurable time delay. Research by Daniel Gruss shows that this unmerging process creates a measurable physical event. By timing how long the memory takes to respond, an attacker can detect whether specific data is present in a shared page. By optimizing for efficiency, the system inadvertently creates a hardware-level side channel. Attackers monitor these minute physical delays to bridge the gap between strictly isolated virtual environments. To exploit this, an attacker measures the exact time it takes for memory operations to complete during standard interactions with a target server. A distinct latency spike occurs when a deduplicated page is accessed against the flat baseline of standard memory. This confirms a cryptographic key fragment exists. By mapping these spikes, attackers pinpoint hidden data, bypassing randomization techniques without executing code on the target host. The process involves sending continuous remote network probes to the target, collecting massive volumes of timing variations to map the system's memory architecture. Historically, this manual timing analysis was impractical due to network noise and fluctuating server loads, which masked the signal. Machine learning models now eliminate this friction. An AI can filter out irrelevant network noise and isolate genuine latency patterns, even as system loads vary. AI transforms a tedious, theoretical side-channel vulnerability into a reliable, automated tool for remote intelligence gathering. While deduplication is a software behavior, the hardware architecture itself presents a different threat vector: high-speed interfaces like Thunderbolt and PCIe. Normally, peripheral data passes through the CPU and operating system kernel, which verify permissions before allowing access to system RAM. But for high throughput, direct memory access, or DMA, allows peripherals to read and write directly to RAM, bypassing CPU security checks entirely. Research shows a malicious peripheral device can hijack this path. Once connected, it autonomously reads or modifies arbitrary regions of the computer's memory. Because the host CPU is circumvented, all OS-level user authentication, access control policies, and memory encryption protocols are rendered useless. This attack requires a brief window of physical access. An attacker connects a DMA-capable device during a maintenance window, and it immediately begins extracting raw memory data. Hardware-level access dictates the machine's security. Against a DMA attack, even a fully patched operating system cannot protect the data in its own RAM. A successful DMA attack produces a raw stream of billions of hexadecimal values, representing the physical state of the machine at a single moment. The hardware extraction is a mechanical process. It pulls data indiscriminately. Making sense of that data requires high-level analytical intelligence. Attackers deploy machine learning models post-extraction to rapidly parse and classify the dump. The AI isolates high-value targets from the noise. Within seconds, it can identify keys buried in the raw hex. While the DMA hardware provides physical access, the AI provides the speed needed to weaponize the data before defenders identify the breach. Endpoint security specialist Dan Duick outlines a unified threat model that combines these two distinct factors into a single operation. In Phase 1, the adversary uses AI-driven side channels to quietly and remotely map out the exact coordinates of sensitive memory over several weeks. Once coordinates are known, the attacker connects a DMA device, executing a surgical extraction of the targeted memory sector. Standard SIEM dashboards register 0 unauthorized access. Because this transfers outside the CPU, the operating system's internal log files remain blank. This methodology breaks traditional digital forensics. The entire lifecycle of the attack exists strictly outside the operating system stack. Defending against this requires a change in forensic strategy. Investigators must look beyond software logs and begin monitoring for subtle timing anomalies and automated probing behavior. The immediate software mitigation is to restrict or disable memory deduplication in sensitive environments to enforce strict tenant isolation. On the hardware side, organizations must properly configure input-output memory management units, or IOMMUs. These act as hardware-level gatekeepers that control and block unauthorized DMA requests. As adversaries automate their reconnaissance, defenders must adopt machine learning to detect the unusual timing patterns generated by offensive AI. Effective defense now centers on treating physical memory mechanics and hardware behaviors as first-class citizens in enterprise threat modeling. The battleground has moved below the operating system. Our defensive strategies must follow.